Hello and welcome to this first video of the M3 chapter Elastic Strings and Springs. No starter here, we're going to jump straight in. This first video we're going to look at Hooke's law, solving some equilibrium problems. In the second video we'll look at dynamics problems. Then we'll determine elastic potential energy. And in the last video we'll use that elastic potential energy together with the other forms of energy to solve problems using the principle of conservation of mechanical energy. So in this video, we're going to look at Hooke's law first, and then solve some problems. In this chapter, we're considering two types of objects. You need to be able to recognize these two. We've got elastic strings and elastic springs. An elastic string can be stretched, but cannot be compressed. Here, you can imagine something like a rubber band. So we've got a piece of string, it's elastic, so it can be stretched out in these directions here. But if you try to compress it by pushing in this way, all you're going to do is make the string slack. However, an elastic spring can stretch or compress. And here, something that's kind of coiled like this, you can pull it out this way, or you can also push it in this way. Both of these will create tension. If you push in and compress it, you might call it thrust rather than tension, but we'll be calculating these in the same way. So if it's a string, it can stretch, but it won't compress. If at any point it looks like it's going to compress, it will just go slack. This is important if I turn these around, put them vertical. For example, if there's a ball on the end of the string here, and the ball goes this direction, then when the string goes slack, the ball will be moving under gravity only. However, if you've got a spring like this with a ball on the end, and that goes this direction, there will still be tension in the spring as it compresses. So there's a subtle but very important difference between these two words. We have a few more bits of terminology to go through. The length of the string or spring without any tension, which I'll call T, is called its natural length. The natural length will be called L. So this is the starting length before you've stretched the string or the spring, or before you've compressed the spring. This is what it would be without any tension. Then if you have extended it or compressed it, the extension X is the difference between the stretched length and the natural length, or the compressed length and the natural length. So X is specifically the extension. To find the total length of the spring as it's extended, then you would have to add the natural length with the extension, and you should be careful with that because sometimes the question will ask you just for the extension and sometimes it will ask you for the total length, which will be these two together. Finally, we need to consider something about the string or spring itself, because every string or spring has an amount of elasticity specific to it, how much it will or will not stretch. And we call this the modulus of elasticity, lambda. And this is taking into account things like the material that it's made from, how thick it is, how tightly wound the coils of a spring are, all of these things that have an effect on how easy it is to stretch this string or spring. We're going to put it all together as a property of this specific thing and call it lambda. So lambda will be different for every spring or string unless the question specifically tells you that two springs have the same modulus of elasticity. And Hooke's law, which is what this chapter is all about, takes these four things, the tension, the natural length, the extension, and the modulus of elasticity, and puts them all together as a nice little relationship. Hooke here is Robert Hooke, quite an impressive scientist in his day, worth looking up if you're interested in historical characters. Through his experimentation, he found the relationship between these four things to be this. The tension in the string or spring at any given extension is equal to the modulus of elasticity times the extension divided by the natural length. I quite like to think of it in terms of the extension though. I think if I want a greater extension, I can increase the tension, i.e. I can pull harder. I can increase the natural length, which means a longer string or spring will stretch more easily, or I can decrease the modulus of elasticity. And sometimes this is considered how stretchy a string or spring is, but because I have to decrease this number to get a greater extension, I tend to think of it more as how stiff the string or spring is. So the lower this number is, the more easily I can extend the spring or string. The higher this is, the harder it is to extend. And if we consider the units for a moment, we can see that the modulus of elasticity must have the same units as force, which is newtons, because here we've got extension, which is a length, natural length, which is obviously a length as well, so the units there cancel out. Newtons on this side must equal newtons here with the modulus of elasticity. And thinking about cancelling out, if you let x, the extension, equal the natural length, so you're doubling the length of the string or spring, then these two do completely cancel out, and you end up with tension equals lambda. So one way to view this lambda here is the amount of force needed to double the length of the spring or string. Okay, it's getting really quite annoying to say spring or string. Generally in the notes, if I say one of them, I also mean the other one, except when compressing. Compressing only applies to springs. But we have this same relationship whether we're extending or compressing. So this is the key formula that we're going to be applying in the examples. You need to be able to apply this formula in a few different situations. In this video we're going to focus on equilibrium problems. We'll look at dynamics problems in the next video. So here's our first one. An elastic string of natural length 3 meters and modulus of elasticity 36 newtons has one end fixed. Particle of mass 2 kilograms is attached to the other end and hangs at rest. This phrase here tells us that it is vertical. So if I draw this out, this is a string, so I'll draw it with a straight line, particle on the end, and that is 2 kilograms. So we've got 2g acting downwards, and there will be tension in the string. It's fixed here, and it hangs at rest. So it's in equilibrium, and we need to find the extension of the string. So listing out the things we know the natural length is 3, the modulus of elasticity is 36, we know that tension is equal to lambda x over L, and we want to find x. To do that, we need to find t first. We can do that by resolving vertically. Here we've got t minus 2g must equal 0 because it's not moving vertically, so t must equal 2g. Now we can use Hooke's law, where t is equal to lambda x over L, putting in the things we know. 2g is equal to 36x divided by 3. And if I put all of that on my calculator with g equals 9.8, that gives x is equal to 1.63333. So to two significant figures, 1.6, and this is meters. And there we have our first answer. Second example, an elastic spring of natural length 1.25 meters has one end attached to a fixed point. A horizontal force of magnitude 8 newtons is applied to the other end, so this is going this way, and compresses the spring to a length of 0.8 meters. So we've got 8 newtons being applied here, and the spring is attached, it's fixed here, so that the spring compresses as this force is being applied. Remember, if this was a string, it would not compress, it would just go slack. Find the modulus of elasticity of the spring. So we're considering our forces first. Here in the spring, again, we've got a tension, or because it's being compressed, I could call that a thrust. But either way, I'm going to use a T to represent that. And if it's in equilibrium, then T must equal 8 newtons. Also, we know that the natural length is 1.25, and the extension, the difference between the length it's at now and the natural length, is the difference between 0.8 and 1.25. So how far is it being compressed? And you might hear me use the word extension or extended by mistake in a compression question. It doesn't really matter. What we just want is the absolute value, the distance between the natural length and the final length we're at, whether that's an extension or a compression. So here we've got 0.45. So x is equal to 0.45. And of course we know Hooke's law, t is equal to lambda x over L, and we want to find lambda. So lambda is equal to TL over x, and that is 8 times 1.25 divided by 0.45, which gives me 22.2 recurring, or as an exact answer, 200 over 9 newtons. Next example. The elastic springs PQ and QR are joined together at Q to form one long spring. The spring PQ, the first one, has natural length 1.6, modulus of elasticity 20. The spring QR, the second one, has natural length 1.4 and modulus of elasticity 28. So these are two different springs, but they're being connected on one end. The ends P and R of the long spring are then attached to two fixed points which are 4 meters apart. Find the tension in the combined spring. So there's a little clue here that the tension is going to be equal in both springs. Although they're different springs, we have a single tension to find in the combined spring. So if I draw this out, I might draw something like this. So this is fixed here, this one is fixed here, so we've got P, Q and R. We know PQ has natural length 1.6 and lambda is equal to 20, and QR natural length 1.4 and lambda is equal to 28. So here we have a little bit of a problem because we know that there is an extension from P to R is 4 meters, but the combined natural length is only 3 meters, so there's a meter's worth of extension, but we don't know how much of that meter extension is here and how much of it is here. So we also have an extension, but we're not sure what that is yet. We know it's probably different, so let me call that x1 and x2. But what we also know, as we said when reading it here, is that the tension in the combined spring is the same tension throughout. The tension pulling this way on this spring must be equal and opposite to the tension pulling this way on this spring, assuming it's in equilibrium. That means when we form our equation, T is equal to lambda x1 over L here, and T is equal to lambda x2 over L here, this T and this T are the same T. So we can combine these two together. And you might think, well, that's not very helpful because we still have two things we don't know, but we have another relationship between x1 and x2, and that is that the total extension is 1 meter. If I make that clear on the side, we've got 4 meters between P and R, minus the natural length of PQ, which is 1.6, plus the natural length of QR, 1.4, equals 1 meter of extension. Another way of writing that, x1 plus x2 is equal to 1, so x2 is equal to 1 minus x1. If you wanted to avoid writing x1 and x2, you could have done all of this using this relationship initially and saying x here and 1 minus x here, which would bring you to this same point that I'm going to write next, and that is that this must equal this with x2 equal to 1 minus x1. So putting all those together, we get 20 x1 over 1.6 must equal 28 1 minus x1 over 1.4. Rearranging that a little bit gives us 5x1 is equal to 8 minus 8x1. So x1 is equal to 8 over 13. From here we could find x2 as well if we like. Obviously that's 5 over 13. But although we need the extension for the question, what we want to find is the tension. So I'm going to put that straight back in here and find T. And doing that gives me a final answer of 100 over 13 newtons, or 7.69 to 3 significant figures. So an important point in here, if you've got one long spring from two combined springs like this, then the tension is the same throughout the combined spring. And although you've got two extensions you don't know, you can write them both in terms of the same unknown variable x, or like I've done here, write them as two separate variables, and then remember that they are connected by that extension overall. Next example. An elastic string of natural length 2L and modulus of elasticity 4mg is stretched between 2 points A and B. The points are on the same horizontal level, and AB is 2L. If I was being picky here, I would say it isn't technically stretched yet, because 2L is its natural length, but it's just on the point of being stretched. A particle P is attached to the midpoint of the string and hangs in equilibrium with both parts of the string, making an angle of 30 degrees with the line AB. So what we've got here is something that looks kind of like this, where this was the line AB here, and although it was at its full length, it wasn't quite stretched along there. That was 2L in distance. But now that there's a particle here hanging down, this must be a stretched string here. Find, in terms of m, the mass of the particle. So if I call the mass of the particle capital M, the modulus of elasticity is equal to 4 times little mg. Natural length is equal to 2L. It's a strange way of writing it, so I'm going to use capital L here instead of little l. And the other thing we know is that the angle here is 30 degrees. What we're doing here, again, is to consider the forces. So I'm going to call this T, and this T, and they will be the same T because it's the same string. So lambda is the same, and midpoint here means that these two natural lengths will be the same if I consider them as if they were two separate identical strings. So for one of those two, I would have lambda is equal to 4mg still. The natural length would just be L. The extension, I can work out with a bit of Pythagoras, would be half of this. So we would have L divided by cosine 30, which is 2 root 3 over 3L. So the extension becomes 2 root 3 over 3 minus 1L. So what I've done there is just use a bit of Pythagoras to find this length in terms of L, and then said, okay, if this was the original length L, we've stretched it to this minus this is the extension. And it's looking a little bit messy, but I do have T at this point. So T is equal to lambda x over L, 4mg times x, 2 root 3 over 3 minus 1L over L, which is just L, and the two L's cancel out. And I can simplify that slightly. 4mg 2 root 3 minus 3 over 3. And then I can resolve vertically and say t sine of 30 from this side plus t sine 30 from this side must equal mg, because it hangs in equilibrium. So resolving vertically, we get t sine 30 plus another t sine 30, so 2t sine 30 minus mg must equal 0. Sine of 30 is a half, so the sine of 30 and the 2 cancel out, and we get t is equal to mg. So this thing here is equal to capital M times g. So we've got 4mg, 2 root 3 minus 3 over 3 must equal mg. We can cancel the two g's, so we get capital M in terms of little m is 4m 2 root 3 minus 3 over 3, which is a fairly horrible answer, and in decimal form would be 0.619 to 3 significant figures. Next example. An elastic string has natural length 2 meters and modulus of elasticity in 98 newtons. One end of the string is attached to a fixed point O, and the other end is attached to a particle P of mass 4 kilograms. The particle is held in equilibrium by a horizontal force of magnitude 28 newtons, with OP making an angle theta with the vertical. Find the value of theta and the length OP. So we've got our fixed point O up here, and there's a string coming down with a particle attached on the end. However, it's being held in equilibrium by a horizontal force. So it's coming out this direction here. We still have a downward vertical for mg, horizontal force of 28 newtons, and with the downward vertical angle theta. Considering our forces as usual, we've got the tension in the string here, and then we can resolve horizontally and vertically. It's in equilibrium, so resolving vertically, we've got t cos theta is equal to 4g, and resolving horizontally, t sine theta must equal 28 newtons. We've also got Hooke's law, so t is equal to lambda x over L, where we know lambda and we know L. So lambda is 98 and L is 2 meters. This is all the information we've got and all the information we need, because we are going to try and find theta and the length. So if we want the length OP, we're going to need the extension on top of the natural length. To find the extension, we're going to need tension, but here we've got two simultaneous equations, so we can solve for theta and t from these two without any problem. Dividing the bottom one by the top one, we get tan theta is equal to 28 over 4g. Using g is equal to 9.8, we get theta is equal to 35.5 degrees to one decimal place. And putting that back in gives me a tension of 48.17 ... Remember, don't use the rounded answers in the calculation. That in turn must equal lambda 98 times x divided by L, which is 2, giving x to be 0.983 ... Add that on to the natural length of 2 meters to give the total length OP to be 2.983 ... And because we've used g as 9.8, I should probably round that to 2 significant figures. 2 more examples to go. 2 identical elastic springs PQ and QR each have natural length L and modulus of elasticity 2mg. The springs are joined together at Q, so this is not dissimilar to one that we had earlier. Their other ends, P and R, are attached to fixed points, with P being 4L vertically above R. So now it is a little bit different. We're looking vertically. A particle of mass m is attached at Q and hangs at rest in equilibrium. Find the distance of the particle below P. So let's draw this out. We've got P up here, a spring here, mass in the middle, at Q, next spring here, fixed down here at R, where P to R is 4L, and the natural length of the two springs is L. So the distances here are very important. We need to get these right, and as I said but didn't do in the other example like this, I'm going to do one extension in terms of the other so that we've only got the one unknown. So it will look a little bit different. What I'm going to do here is have my 4L from here to here split into pieces. We're going to have L, which is the natural length PQ. Then we have another L here, which is the natural length of QR, because they're identical with natural length L. And then obviously in the middle here we've got 2 more L's to go. And we don't know how much of that is here and how much of that is here. In fact, we don't even know if this is a full L. This could be all the way down compressing, but if that's the case, all we'll do is end up with a negative answer somewhere in there to show that that's in the opposite direction to what we thought. So assuming that this is still a little bit extended, I'm going to write not x1 and x2 like I had before, but x and 2L minus x. So I'll have x here, the extension of PQ, and here the extension of RQ, or potentially the compression, is going to be 2L minus x. And you could do what I did in the previous one, x1 here, x2 here, and then connect them with x1 plus x2 equals 2L, and of course you'll end up with the same answer at the end. We still need to consider our forces though. Here we've got a tension going this way. Here we've got a weight going this way, and that is mg. And here, on the assumption that it is still extended, not compressed, we've got a tension going this way. However, if we find that this is negative, this also would be negative, and it would be pushing upwards. Because these are different tensions, I will now call this T1 and this T2. Because unlike the extension, I can't write one of these in terms of the other. I don't have that much information about them yet. So it's all hanging and resting in equilibrium, and we need to find the distance of the particle below P. So we want to find this distance here, which means we're trying to find x, and then we can just add that to L. To find x, I'm going to be forming Hooke's law equations. T1 here is equal to a lambda 2mg, because they both have lambda is equal to 2mg, they're identical springs, times by the extension of PQ, which is x, divided by the natural length, which is L. T2 is equal to the 2mg again, times the extension, not x this time, but 2L minus x, divided by the natural length, which was L as well. Now I've got my two forces, each with an x, and the x is the thing I want to find, so I need to be able to get these two together, and to do that I can use resolving forces. In equilibrium, T1 must equal mg plus T2. So by resolving vertically, I can say T1 minus mg minus T2 must equal 0 equals mg plus T2. And that will get these two in the same equation, so I can solve for x. So we have 2mgx over L is equal to mg plus T2, 2mg times 2L minus x all over L, and now I just solve for x. I can cancel mg from each term, multiply through by L to put an L here, so that gives me 2x is equal to L plus, if I expand this out, 4L minus 2x. Bring that over, we get 4x is equal to 5L, so x is equal to 5L over 4. Remembering that we want the distance below P, so it's not just the extension, but the extension x plus L. I need to add L onto this. 5L over 4 plus 1L will give me a distance PQ. 5L over 4 plus L is equal to 9L over 4. And that is the final answer. Last example of the video. We've got one end A of a light elastic string AB, so a string, not a spring, of natural length 0.6, modulus of elasticity 10. That is attached to a point on a fixed rough plane, and the plane is inclined at an angle theta to the horizontal, where sine theta equals this. Remember, once you know sine theta is equal to 4 over 5, recognizing 4 and 5 as two of your Pythagorean triple 3, 4, 5, you should be able to write down that cosine theta is 3 over 5, and tan theta is equal to 4 over 3. A ball of mass 3 kilograms is attached to the other end of the string. Okay, I better start drawing this, otherwise I'm going to get lost before we even begin. So we've got a plane inclined at theta. One end is attached, that's A, so let's put that here. And the string is attached there, coming down the plane, and there's a ball on the end of the string of mass 3 kilograms. So we've got m is equal to 3, then we're told the coefficient of friction, mu, is equal to 1/3 between the ball and the plane. The ball rests in limiting equilibrium, so friction is equal to, not less than, mu times r. It's on the point of sliding down the plane, which means friction is acting up the plane, as is the tension in the string, with AB along the line of greatest slope. Find the tension in the string and the length of the string. Okay, that's a lot of words, and I've done a lot of work already as I've gone through it, creating the diagram here with the forces, getting the angles here, and a key point here. To me this looks a lot like force diagrams like we've had before. The only difference here is that this is a stretched string, not a fixed inelastic string. So we're going to do a lot of what we normally would do. We know the friction is equal to mu times r, so I need to know r here, and that is equal to the component of the weight. The weight is 3g. Component of the weight here is 3g cos theta, so r is equal to 3g cos theta because it's in equilibrium. The component down the plane, 3g sine theta. Now we can find friction by using mu times r, where we know r from resolving this way, and we can resolve this way down the plane to give a connection between friction, tension, and this component of the weight. That will give us the tension in the string from a forces point of view, and then looking at it from Hooke's law, we can use that tension to find the length of the string by finding the extension and adding it onto the natural length. So let me finish off here. Mu is equal to 1/3, and we know that r is equal to 3g cosine theta. The 3's cancel, and cosine theta we know is 3/5, so that's 3g over 5 for the friction. Then resolving down the plane, so if I put resolving parallel to the plane, we've got t plus friction must equal 3g sine theta. We know friction is 3g over 5. We know sine theta is 4/5, so this becomes 12g over 5. And we still have tension on this side, so the tension is equal to 9g over 5, or 17.64, with g is equal to 9.8. So to two significant figures, that would be 18 newtons. We also need to know the length of the string, though, so I'm going to also combine this known t in Hooke's law with lambda x over L. So that gives us 9g over 5 must equal to lambda 10 times x over L 0.6. Solving that for x, and g is equal to 9.8 gives us x is equal to 1.0584. And to get the length, I then also need to add that on to the 0.6 natural length of the string. So you get 0.6 plus 1.0584 to give 1.6584, and I've used g as 9.8 down here, so I should round that to two significant figures, 1.7 meters. So I hope a lot of that work was familiar from previous chapters, previous modules. The only difference here is that we've got the tension using Hooke's law to find the length of the string as well. Part B says if mu is greater than 1/3, without doing any further calculation, state how your answer to part A would change. So you just have to think through what this would do. If mu is greater than 1/3, that means there would be a greater amount of friction. If friction is greater, then to balance this 3g sine theta, which wouldn't change, there does not need to be as much tension. If there is not as much tension, then this number is less. If this number is less, then the extension is less, and the string would not be as long, it would not have stretched as much, the ball would be slightly further up the plane, and the length here would be slightly less. So the answer to this part, although I won't write it out, the tension would decrease and the length of the string would decrease. Quite a few examples there. I hope that's enough now for you to have a go at the exercise 2A. Maybe I'll see you in the next video.